I think we can start our discussion session. And I can start first. I mean, my mind is still in the loop about the talk, like all the principles about security and how we can connect them and applying them to the machine learning security and privacy problems we have currently. One quick question, direct question regarding the privacy issue here for Smash is that like for the instant hide, for example, people in the a lot of discussion.
They have a clever name, insta hide, not instant hide.
Okay, insta hide. Sorry. Yeah. So they have a lot of discussions about they didn't prove differential privacy and etc. Do you think differential privacy is actually enough for this work? Because to me, I feel if as the attack you propose, it will be the kind of model inversion rather than membership attack, right? So, differential privacy is enough for the guarantee here, or what is?
No, let me be careful. I'm not saying differential privacy is the only definition in the world, okay? But we should be striving for at least having a formal definition and having some sort of an argument saying that, look, if you break my system, you violate this assumption or solve some hard problem or something like that. But I'll tell you, it's even worse. I was at NUDIPS before the pandemic. I think was it Vancouver. I think everything is
yes,
pandemic. And I was talking to some guy who had an ML defense paper, and he didn't even know. I said, "Oh, you didn't define your threat model," and he said, "What's a threat model?" So I think that it is a much but I didn't know. But I didn't want to say that differential privacy is the only definition out there. But we should be at least striving to have a formal definition and say that if you can if this attack is successful on your scheme, then you will violate this assumption or something like that. But no, I'm not saying differential privacy is the only definition in town.
Sure. Yeah, definitely. That's great. Thank you. Yeah, I think there is a question from Nikita in the chat. Is there any reason that we believe ML will be? Yeah, go ahead, Nikita.
Yeah, I just saw Nikita. So I even though my PhD was in model checking and formal methods, I don't want to say that everybody should be writing proofs. Okay, this is not what I'm saying. At least even in system security papers, and Nikita, you can we can discuss this, but they do have a threat model and some sort of an argument, maybe even in English, which sort of says, hey, if an adversary with this threat model can break this, then that means they must have tampered with the TCB, or they would have to have touched my protected memory. To me, even that is missing. I mean, Zico can correct me, but even that kind of, and I didn't mean to say argument.
No, I agree. I think that's pretty important. But I think there's sort of the formal side of things has always been. It feels like it's been a desiderata in security for a long time, but it's not really there in much depth in most security research. With some exceptions. I mean, differential privacy certainly has a nice formal way of thinking about it, and a lot of cryptography has really clear assumptions. But a lot of it is definitely, there's discussion about models, a discussion before, but it's a much less formal way than I think when we think about cryptography.
Yes, I agree. I didn't. Is the question saying that I should not have said proof? I should have just said argument or something like that? Or?
Maybe. I think I wanted to clarify a little bit about what you're hoping to get what are you hoping to bring from the security community, just because I think when you talk about proofs and underlying assumptions, that's not really representative of large chunks of the security research.
That's a fair point.
Mm-hmm. Yeah, that's very indeed intriguing. We hope we get some guarantees for either security and privacy. I think in like Smash Talk, this privacy perspective about guarantee, and in this code talk, we have the guarantee from the like robustness and the security perspective. Like yeah,
no, but I will tell you this. This is I would love to get Zico's thought on it. Privacy is slightly different. So think about I'm a clinic, okay? Mm-hmm. I'm a clinic, and I say, oh, InstaHide authors, they're from Princeton. Princeton is Ivy League. You know, I take their scheme, I encode my images, and now I put it in public. Okay? You cannot blame a clinic. I mean, they are not CS people, right? It is actually, that is the biggest danger. So the danger, I think, with privacy is more than putting stickers on a stop sign. Because the idea is that this will be publicly released, and then that stays in perpetuity forever, right? And in fact, believe it or not, there was somebody from the medical school here. They said, oh, we tried DPSGD and that just like totally crapped our model. Why can't we use this InstaHide thing and just release our data set to the world? See, that is the bigger problem in privacy, because once you release that data set, that's there in perpetuity. It's there. It's all over the place. I think that so it's a much more, these attacks are much more powerful on these privacy preserving. I don't know what the correct term is. The privacy preserving ML type systems.
I would just say that I mean I think it depends on what system is being broken. So if there were a break, so the nature of adversarial attacks, I think, the extent to which it is a genuine security flaw depends on the nature of the classifier hugely, right? Because if it's a classifier that does not expect to process sensitive information where you have full control over the inputs and outputs in the system, then it doesn't really matter if your model is robust or not. On the flip side, if you were, and I mean, I used the example, because I think it's a pertinent one. I mean, Face ID on iPhones uses deep networks, right? That's how they identify who you are. And I mean, and talking with people at Apple, they actually admit that if I had the network structure for Face ID, I could probably design an adversarial patch that would unlock Face ID, right? Maybe. And I don't know how on the record that is. So it's probably true, right? Just no one uses deep networks, you can probably do it, but that has not been broken, right? So it could be. Right. And if you were, that would have obvious security implications then, right? It's a very, very clear security implications to breaking Face ID. But
you were saying something about NeuroCrypt. How were people able to reverse engineer that?
Neural hash.
Neural hash, sorry.
This is, there's been a bunch of Twitter posts about this recently. So I think 3 people simultaneously all did this. So neural hash was this Apple library for basically taking perceptual hashes of images. It was an Apple library for taking, I guess, yeah. So when it comes to, so someone pointed, we assume Face ID has not been broken yet, but neural hash hasn't been broken. So neural hash was an Apple library for perceptual hashing of images. And hash functions should be very hard to find hash collisions, right? Because you should be able to, I think part of the goal of it was to identify illegal content, legal images on people's iCloud files, right, and things like this, without actually ever looking at the files themselves. You just share the neural hashes, and then they can identify illegal things from this. Basically, several groups simultaneously. So one group discovered they could extract the model, so that they figured out how to get the actual model somehow from, because unlike other things that sort of are a bit more, I'm not sure where the Face ID model is stored, but this model could somehow be extracted one way or another, because I think it was meant to be run like in the cloud or in some environment you control. They extracted the model, they got the model, and then basically everyone in the world broke it through adversarial attacks, right? So I'll through the next question, I'm not talking, I'll find a link to some of the, I think it's like literally released on Twitter, but there's a bunch of GitHub repos also that sort of break these things. So that's a genuine break too, right? With adversarial attacks, right? You're basically what they're doing is they're finding other images that collide with the hash. So you could either this implies, of course, you could either manipulate illegal content to look like some benign content, or you could find just you shouldn't be able to find collisions of the hash function that easily, right? So the bigger point I would say is that I think that the notion to which adversarial attacks imply security issues is very dependent on the nature of the classifier itself. Because if this is something related to security, then it's very clearly a security issue. I would say probably privacy, as you say, has this characteristic mainly because privacy is almost always treated as a security implication, right? Whereas, all machine learning classifiers are not always treated with sort of security implications. Whereas privacy built into it has a security implication. And so this is where I would sort of agree that it's hard to think of applications of privacy that aren't somehow related to security. And so therefore a break would impact these things. Whereas for ML classifiers, there's a whole spectrum.
So you say kind of baked into the problem itself.
Yes. Whereas there's a lot of machine learning systems where security is not baked into the actual runtime deployment of the system. It's in a closed environment where you have control over the inputs, and so therefore it's really not in the same way baked in.
Great.
Yeah, that's a very interesting.
Yeah, that created that whole PSI system from Apple created a huge firestorm.
Yeah, I just find a link. Previously, I think people hacked the Face ID and do some 3D print the face, etc.
Yeah. So this is actually a good point. So yeah. There are there have been some purported breaks of Face ID or Tesla's driving system too. So there was also some Israeli security firm that sort of put little dots on the road that Tesla thought was like a lane marker or something like that. Mm-hmm. I would actually argue that the mask problem is a very hard one to solve. If I can construct a perfect 3D reconstruction of someone else's face, I mean, that it's trying to detect that. So is it really being broken? So the question of adversarial example versus not to some extent, I think, is not like, is the underlying system broken in some way? It's the nature of adversarial examples is that these are things that are obviously do not change the characteristic of the image for humans, but change it for the algorithm, right? So a little patch on a stop sign does not change a stop sign for us, but it changes the algorithm's perception. These imperceptible examples do not change the image for us, but they change the algorithm. So I would just say that for like masks and stuff, I would argue that like I would be fooled by that too, right? And this is like the Mission Impossible, right? When they take off their masks, like it fools everyone, right? This is the whole point about masks. Whether you guys know that this will actually work that well or not, but I would say sort of an adversarial robustness attack on a system would be a system where it was obviously not the other person. You put a little sticker on your cheek, and all of a sudden I can unlock your cell phone, right? That would be clearly something that should not happen, but I think is probably possible if we had access to the underlying model. Yet it hasn't been broken in that respect with the query access we have, which is definitely not an existence proof of security, which is also why I think to a certain extent you sort of need this sort of fix break setting is actually relevant in some cases, because these are the only ways in which we know these things are secure, right? Or we think that they might be secure. And so I sort of think that there's a distinction there that I would raise, that it has to be a break that is based upon adversarial examples, which by definition are things do not fool humans, but fool the classifier.
Yeah, totally agree. I think that comes to the threat model importance that's mentioned by both of our speakers. Like the threat model from the security perspective now will only be able to get some certain like certification on the level of like LP non-bounded. And from the privacy perspective, it's even more interesting. Recently, we are thinking like for example, in differential privacy, it's trying to hide individual privacy information, but actually publish the statistics on the distribution level. But actually, some distribution level information is also privacy sensitive. Like in a city, how many, like what's the traffic flow, what's like the timing for like a high demanding for the cars and etc. So I think it's really actually indeed, as Sumesh mentioned, also from the privacy perspective, very hard to define the SWAT model. But one idea, I don't know whether our speakers agree here, is that from the security perspective, if we want to protect privacy and security, we need to stick to certain SWAT model. And maybe they are domain specific by definition, or maybe depend on some constraints for the attackers, etc., like the query number they can access, etc. Otherwise, it's almost like very hard to get the protection.
I agree with what you want to do. It's almost like you want to do concrete. In cryptography, there are like two analysis, right? Asymptotic and sort of a concrete analysis. Kind of think Dan Bonnet, think Mir Bellare. But I think the concrete analysis will be very hard. I don't know if Zico can, I mean, like saying, oh, I can prove that you need quadratic number of queries to get this adversarial example, because I don't think we understand that much about learning.
It's I don't think we understand enough about query complexity, because the query complexity deals fundamentally. I mean, and also hard query, especially if you only get a hard label, then it's almost impossible to say anything, because you don't even have a continuous service anymore. So how would you ever know like how many queries you needed? I could, so I can't imagine how you could possibly get a sort of place a upper bound on the number of queries you would need, because you could always sort of, search forever and not find anything relevant, right? That's always possible. And I don't also know how you could get a lower bound on it, because I feel like it's always possible. Like it might be the case that 2 sample points would point you in the exact right direction. So it's very unclear to even know how you could ever upper bound or lower bound on the number of queries you would need to find an adversarial attack. It just seems very, very hard.
But I think it is a good goal, but Bo, I think it will be extremely hard to do any concrete analysis like that. I'm not saying we should give up, but it's not easy.
Yeah, I think we need to have layer and layer assumptions, then we can achieve something for that. I think we have some assumption for like black box and the model smoothness, etc. Then we have some upper bound for the query complexity for black box attacks, but that need a lot of assumptions and maybe not quite realistic either. I see. I think since we are here, I think I also have one question regarding the security and privacy, because we talk a lot about this, and this workshop is also about security and privacy. I think there should be one like point or certain point to join them, so that we can have something like a unified theory or some fundamental problem we want to address, rather than, of course, we still focus on each concrete problem, but there should be a final goal that we want to tackle. To me, my very shallow understanding and opinion is that, do you think essentially the generalization is a fundamental like connection between these different types of security and privacy problems?
Like a grand challenge kind of a problem? Is that
yes, exactly. What do you think it would be? That I think that will help a lot of like our students and researchers here in the group. If you have comments on that, like what's a grand challenge or fundamental issues of the security and privacy? Because, for example, from the security perspective, I think one fundamental issue is the distribution drift, right? Like the poisoning attack and the evasion attack. Indeed, they are considering different, like time drifting at different time point during machine learning models. From privacy, it's also related. Do you have other comments?
Let me, Zico, if you have I'm thinking if you have some
grand challenge. I mean, I think as much as I sort of feel that it has its limitations, I do think that there's still the obvious challenge of producing more robust models to known threat to sort of to known well-specified threat models, right? And it's not a solved problem, and it is in some sense still a grand challenge. And regardless of whether or not we really want this, I think this is still something we really do need to solve to better understand robustness and better understand just the feasibility of the whole endeavor that we're sort of talking about here. And if there is a breakthrough, that would be enormously potentially substantial for the whole field. I have a hard, so I think on the flip side, I do think that most of the grand challenges I see would be related to the break of models in the wild with adversarial attack methods, and these are not easy, right? So just given the fact that we have these systems that are using this, FaceID being one example, right? Make a a inch by inch sticker you can put on your cheek, which will break FaceID, which will let you open someone else's phone, right? Ideally, anyone else's phone. That would be extra credit if you can open anyone's phone. I think that that would have massive ramifications, right? If this was possible. I sort of would see that as a really important challenge from the adversarial perspective of security. And beyond those, I think just making large, practically speaking, almost all of our robust models are incredibly unscalable relative to traditional models, right? So it takes hundreds of times longer to train potentially.
Well, even for private model like DPSGD, right?
Yeah, that too. But ignoring that, even just talking about literally just like trying to train an adversarial robust model on ImageNet, it takes forever. So just building, something that matched our performance of the best robust models, but doing it in a fashion that was as fast as training traditional networks would also be a huge and important advance in the field.
Well, you had a paper on it, right?
Yeah, but again, it doesn't quite match the best performance. We try to get closer, but it still lags behind, and still, frankly, even on ImageNet, it still lies behind the one step, and it's still like twice as expensive. So it's 2 to 3 times as expensive because you have to do one adversarial step each time. Actually, no, it's more than that because you have to do one prediction, one gradient, and one adversarial step. So it's like about 3 times as slow. And in some sense, you can't do any better than that, right? That's a sort of a hard limit, right? And doesn't work as well as sort of the more fine grained stuff. So I think that having really something that was robust somehow by construction, that therefore didn't need these same, one-step adversarial updates, which we know also can be broken under the right circumstances, would be an important avenue to pursue.
I'll throw out a challenge problem, which is not mine, but I heard it at a crypto keynote. I think Shafi Golwasser or somebody. So so right now our attacker basically is information theoretic, right? It can do basically anything. We don't put any computational bound on it. And we know if you take analogy to information theory, we know that, if you look at old work of Shannon, if you have an information theory attack for perfect secrecy, you need key space as large as message space, right? And so that's why in modern crypto, everything is sort of PPTA attacker and so on. So for example, could there be a robust network where you say that, okay, for a PPT attacker with some security parameter, it takes a long time. If you can sort of say, hey, to get this kind of an attack that fools my system, it will take 30 years. Well, I would definitely be gone by then. And, I wouldn't care if you break my ML system in 30 years. I would say, okay, go for it. So I think that would be sort of can there be a crypto-style computational version of the robustness of ML models? Which I don't know. I'm just drawing analogy from crypto. This was kind of a challenge problem. I heard one of I think it was Shafi Goldwasser's one of her keynote talks, and she said, "Can we bring that kind of a mindset here?" But that's
so I really like this idea too, and but I would just sort of point out that the challenge of these things is less about sort of solving that properly would be such a change to the paradigms of which we currently build deep learning systems, right? So it'd be fantastic if we could. I would just say that, and so it is in the same sense a grand challenge. But to be clear, we have no idea how to build those kinds of properties into current machine learning systems. So it would require an advance in much the same way, yeah.
Well, but I will just give you one little tidbit. If you look at all of the hardness results in learning, saying, oh, it is hard to learn something, they're all based on crypto assumptions, like one-way functions and so on. So there is something going on there. But in any case, you're right. We don't, for current systems, they all want to do is keep increasing capacity, keep getting better accuracy.
Yeah. That's very insightful discussion. I was thinking about this for a long time. I think one potential solution I'm thinking as well is about the threat model still. Like we can assume some threat model, therefore design the system according to that threat model. The computation of the attacker is incomplete or is hard. That is possible. But if it's generic threat model, that will be very hard.
You mean like you have to kind of really limit the threat model?
Yeah, exactly. Limit the threat model to solve certain like linear programming or certain optimization, and then we can optimize the model itself according to that, and therefore the solution for the attacker is indeed challenging. But yeah, otherwise, okay. So yeah, in the end, see any other questions from the audience? Yeah, I think so far we have talked a lot about a single model, like completeness and security privacy, which is already quite challenging. So actually, I was thinking one thing also, I'm also like trying along our discussion. So with the distributed machine learning, making the things like learning protocols more complicated and making the like aggregation protocol, just like a security protocol in traditional, more complicated, maybe that's also one potential way to make at least the distributed learning platforms challenging and more robust. I mean, challenging to the attackers. Do you think that's something possible in your mind?
Are you especially referring to federated learning style?
Yeah, federated have single servers, and maybe some even we don't have a server. We have like a distributed learning with like local servers, like asynchronous communication, etc. So this way, we may have certain MPC protocols from the crypto perspective, and then help to ensure the robustness or privacy. Yeah.
Yeah, I'm not positive about that question.
I see. Okay. Yeah, indeed. I mean, I think towards arbitrary attacker is indeed hard. I think one very concrete question previously I heard for Rico's talk is that in the talk you mentioned, like indeed currently the robustness is very conservative only against the LP norm. I would say maybe some guidance to the student audience here about what's the potential next step, right? Maybe we cannot address all the problem, but maybe some potential next step is robustness, certified robustness against certain distribution of adversaries which have properties of the distribution, or like certain like other types of more concrete threat model rather than being too ambitious. Yeah, what do you think?
Yeah, so we certainly have done some of this work, right? So we are looking at some work on. We've looked at using generative models to specify the distribution over the threat model. So the threat model is a conditional GAN where the latent applied to the image where the latent space is constrained to be within some ball, and then this is then required to be, and then these images look perceptual by the nature of a conditional VAE or something. These models tend to be visually similar to the original one, but have important differences, right? That sort of correlate better with perceptual similarity. The fundamental problem here is that, as I said, the crux of the issue is that, to me, adversarial examples refer to settings where humans are not fooled and algorithms are. And so until we can describe the space of human perceptual similarity, this is somewhat, which by the way would require a deep model, which by the way would be adversarially non-robust, right? It's sort of this chicken and egg problem about how can you define perceptual similarity without humans. So I think there might be an interesting, I mean, I don't know how to do that, right? So yes, you can talk about other threat models that are seem to be more in line with what we mean by perceptual similarity, but I still don't know if this solves the fundamental problem, which is always therefore possible to find things that are not within that threat model that are perceptually similar, and so we can enumerate all those things, right? Which we know the L infinity ball contains all this, right? So we're already talking about a set that's bigger than the L infinity ball. But we somehow don't think this can work, or we somehow still can't solve the problem, right? So I'm not sure if I have been in the past sort of very interested in this sort of perceptual similarity, or looking at other threat models that more accurately capture perceptual similarity. I'm not convinced this really is the solution to the core underlying problem here, but it's still really interesting as another direction of study, especially when you talk about sort of the other. Alex didn't talk about it in talk today, but there's a whole other set of things that sort of robustness can be used for in a more sort of practical sense, like interpretable models and stuff like this. I guess he had a little bit of that, but so I'm not sure. I do somehow think that the notion of, if we were able in any meaningful way to define security against a compute limited adversary, that would be very interesting, right? So if we could bound the computation needed to break something, that would be very interesting. Not even so much for practical reasons, just because it would be connecting how hardness is usually proved for crypto, the ones that have proofs, right? With what we do in machine learning. So I actually think that would be a really interesting, if we can start talking about, are there threat models that you can.
I think you again froze.
Oops, I froze again.
Okay.
No, I don't think I'm frozen. My power didn't go out this time. If there are, or maybe I was just like thinking off in space, right? If there are settings where we can do this, this would be very valuable, because not so much for the practical aspects, but for the unifying worlds aspects. I think it's going to be really hard to sort of define a practical threat model. Mm. So what I'd also be interested in understanding from that perspective is, are there small changes that somehow make these things more robust to kind of a suite of typical attacks with typical threat models, and does that even mean anything in a fundamental way, right? Like it's a really interesting question, right? Because it's unclear, right? What is there any sort of practical partway there security you can get, even if you can't get sort of formal security? And the answer seems to be, doesn't really the answer seems to be no, but I still think it's worth thinking about at least.
Well, I think the issue might be the following, right? I think the thing is whether you use this ML in an autonomous driving car or some other context is very important here. And so, like, look at a crypto's proof, right? If I want to prove my encryption scheme is in CPA secure, once I have proved it, I put my crypto system out there. I don't care what you do with it.
Right.
Right. I mean, you can encrypt packets, you can encrypt images, you can encrypt your bills. I mean, I don't really care. I don't know whether that kind of guarantee can be given for the ML models because they're so context dependent, right? My hunch is on a phone, you care about different things. So it's like a utility and robustness and everything is mixed.
And it's the fact that, I mean, by definition, what was that?
It's a more messy problem, I think.
Yeah, by definition, I mean, the crypto type security would require white box security, I think, right? It would require security where you actually know the model. And that is precisely something that does not seem to work and seems to be ignored because it kind of works okay when you don't do that, right? So things seem to work okay if you don't release the model. I don't know my iPhone's Face ID model, and therefore it seems to work okay, or seems to be reasonably non-broken.
A little bit of correction, Zico. I think what happens in crypto is you will say that they know that I'm using RSA, but they don't know the secret key.
Oh, of course.
So you do know, you in this case, it would be the more analogy will be, you know my architecture, but maybe not some random weights.
The weights, yeah.
But I don't know whether that.
Yeah, I guess it also depends on like what we call an algorithm, right? Whether we call the model like the program itself, or whether we call the training thing the program, or the training the architecture of the program. But okay, that's fair. I still would imagine. Yeah. So you just don't know the random state you initialize the weights, basically, right? Like you know everything else, but you don't. And you know the data. Do you know the? I guess do you even know the data that was used to train the system, the model?
No. I think what would happen is that, I mean, think about it. I'm using my analogy to AES, right? I know how AES works. I know every algorithm of the round and everything. I just don't know the secret key. So I don't know what the analogy there is, but there is something that the attacker doesn't know.
Mm-hmm.
Yeah,
I think it's fair to think of different settings. I think actually codifying these settings better would go a long way to understanding. We've operated in one model, and that model is clearly insecure by any definition of the term, right? And then when we have black box settings where we can query things arbitrarily, then of course it's still insecure because you can just do numerical gradients and get the gradients that way. So of course it's still insecure. And then how do you know that the gradients are like do you really need the full numerical gradients? Can you find like a subset of gradients? It's definitely possible to not have full. So the setting that we're using is one that is inherently insecure, and understanding if there's anything more we can say about a different setting that is slightly more secure is, I think, a really interesting question. And it's very unclear that that's possible though. And most attempts fail.
Yeah, definitely. Yeah, I think also one challenge from applying the security concept to the machine learning is that for security, we have very concrete thing. For example, I have a message. It's a binary, and I want to encrypt it. So from the number theory, I can prove it's hard to decrypt based on some number theory have problem. But in machine learning, we actually want to have a distribution. We want to approximate the distribution, not only a very concrete instance level. And how to, like, what do you mean by encrypt the distribution and hide the information there, or make it private or secure? That's actually quite challenging. And for example, we don't know how to symbolically represent this learning things we have currently. And second of all, what's the distribution can actually, how good the distribution can hide, because it's very generic, not a very concrete, like one message or one vector. So yeah, I think that's really interesting. See if we want to close the gap. If we can close the gap, that will be really exciting. I agree that if we want to do that, maybe we indeed need a big paradigm shift, as you said, about machine learning architectures or things. So we do not learn by backpropagation or things. We may learn by more concrete ways, such that the concrete way of the weights or the parameters can be encrypted, because currently the model is like, even we have a slightly different architecture or model parameters, they perform similarly. So you can still attack one and transfer to the other.
Yeah,
so
but
that's won't help.
But I think Zico had a good point. I mean, it looks like the community just keeps going how they're going. It'll be very hard to kind of shift. I think he said something like that in his talk, and I kind of agree with that. I mean, it looks like, you know, they just keep going, making the models bigger.
Yeah, absolutely. I mean, it's people are deploying machine learning, right? That's what's happening right now, and they're not currently paying a full, like, the price for it, I guess you would say, and whether they will or not, I think will depend on a much more sort of sociological aspect. And basically the question will be, you know, is the minimum cost, or rather, so you know, let's also give sort of like people that are breaking stuff credit. Like the motivation for most large scale security exploits is money in one way or another, right? So what people want to do is they want to make money. Will there be a way to make money by breaking machine learning algorithms that are deployed in practice that is more effective than making money, or at least equally, you know, enough effective such that it's worth someone's time to invest in it?
Yeah, I think the only way this will really get is that if there are real attacks in the wild that have consequences.
Mm-hmm.
I think,
and those will happen when there's a monetary advantage to it.
Yeah.
Yeah. Okay. In the end, there is a question in the chat asking, what if we had the complete training set? Could you also compromise the model built from that? Yeah.
So these are these like transfer attacks, right? And they tend to work pretty well.
Yeah.
So yes.
Yeah, I think that's also indeed the problem. I'm thinking like about difference between machine learning and the security. They have very close things. Okay. I think we are good, and we have very intriguing discussion from other speakers. And our great organizer David Nichol, who is a good security people, also here. I don't know whether you have further comments on that and want to chime in to provide additional thoughts.
Oh, well, just thank you. I think the kind of discussion that you all had and the kind of points that you brought out are exactly the reason for having this kind of workshop. So, you know, I learned a lot about, so thank you for offering your thoughts and participating in this way.
Thank you.
Yeah. Okay. Yeah. Thank you, everyone. Thank you for the great talks, and yeah.
Before we end, is that Lake Michigan? I don't remember that lake in Urbana-Champaign.
I think it's kind
Michigan,
of a lake. I think it's a lake nearby. Actually, I don't know.
Oh, really?
I don't remember. Yeah. I think working from home, we need some very flexible environment. Yeah. Okay. Thank you, everyone. Yeah.
Bye, everyone.
Thank you so much.